September 3rd, 1928, London. A scientist returns from vacation to find his laboratory contaminated. Petri dishes ruined, experiments destroyed. But one plate catches his eye. Around a patch of blue-green mold, bacteria have vanished, dissolved, as if erased by an invisible hand. Alexander Fleming names it penicillin. He publishes his findings. The world yawns. The drug is unstable, impossible to produce. For over a decade, it sits forgotten. A laboratory curiosity gathering dust while millions continue to die from infected wounds. December 1941. America enters World War II. Military planners face a terrifying truth. In the last war, infection killed more soldiers than enemy bullets. Wounded men don't die from shrapnel. They die days later from gangrene, blood poisoning, infections that medicine cannot touch. And America has no answer, no miracle drug, nothing but tourniquets and prayer. But they remember Fleming's forgotten mold. What happens next is impossible. In just 4 years, America transforms a substance that couldn't be produced in a laboratory into an industrial weapon manufactured in factories the size of city blocks. A moldy cantaloupe from an Illinois fruit stand becomes the genetic ancestor of all wartime penicillin. Deep tank fermentation, a technique never tried for medicine, produces billions of units per month. By D-Day 1944, every medic storming Normandy carries vials of penicillin in his aid bag. The results are staggering. 15% fewer deaths from infected wounds. 100,000 soldiers who should have died live. German prisoners, treated with penicillin by American medics, realize they've lost not because of tanks or tactics, but because America has so much abundance, it can afford to heal even its enemy. This is the story of how a contaminated petri dish, an open window, an American industrial might, turned death into survival and saved a generation. September 3rd, 1928, London. St. Mary's Hospital, second floor, where the windows are cracked open to let in the late summer air. Professor Alexander Fleming returns from holiday to find his laboratory in disarray. Petri dishes stacked carelessly. Cultures contaminated, experiments ruined. He begins the tedious work of cleaning up, lifting each plate to the light before discarding it. Then he pauses. One dish, smeared with golden staphylococcus colonies, shows something unusual. Around a patch of blue-green mold, the bacteria have simply vanished, dissolved into nothingness, as if erased by an invisible hand. Fleming does not yet know that this contaminated dish, this accident of poor housekeeping and open windows, will decide the fate of 100,000 soldiers in a war still more than a decade away. He only knows that something in that mold kills bacteria. He scribbles a note in his journal. The world, for now, does not care. Fleming names the substance penicillin after the penicillium mold from which it comes. He publishes his findings in 1929. The British Journal of Experimental Pathology prints his paper, Quiet Indifference. Penicillin is interesting, certainly, a curiosity, but it is unstable, difficult to extract, impossible to produce in quantities large enough to matter. Fleming himself cannot purify it beyond crude liquid filtrates. He tries for a few years, then moves on. The mold is filed away, kept alive in his laboratory like a botanical specimen in a museum, a footnote, a might have been. For over a decade, penicillin remains exactly that, a whisper in medical literature, a compound that works beautifully in a petri dish and nowhere else. The world continues to die of infected wounds, pneumonia, childbed fever, blood poisoning, all the ancient killers that medicine cannot touch. And then the world catches fire. By December 1941, the war has devoured Europe and the Pacific. American boys, farm boys, and factory boys who have never seen an ocean are being packed onto troop ships and taught to hold rifles and throw grenades. The United States military understands one brutal truth. Modern warfare produces modern wounds. Shrapnel tears through muscle. Bullets shatter bone. And in the hours and days after injury, bacteria, invisible, relentless, invade the body and finish what the enemy began. The numbers from the previous war are clear and unforgiving. In World War I, infection killed more American soldiers than German bullets. A man could survive a bayonet wound to the abdomen, only to die a week later from peritonitis. A fractured femur, if the bone pierced the skin, became a death sentence. Gangrene would set in. The leg would blacken, and the infection would spread into the blood. Medics amputated limbs not to save function, but to save lives, and often they failed, even at that. Sulfanilamide drugs, introduced in the late 1930s, help, but only against certain bacteria, and only if administered early. Against Clostridium perfringens, the bacterium that causes gas gangrene, sulfa drugs were almost useless. A soldier with gas gangrene had perhaps 50-50 chance of survival, and those odds required amputation within hours of infection. American military planners in 1941 look at these statistics and understand what they mean. If the United States commits millions of men to combat in Europe, North Africa, and the Pacific, tens of thousands will die, not from enemy action, but from infected wounds. The question is not whether infection will kill soldiers. The question is, how many? And in the winter of 1941, America has no answer, no miracle drug, no industrial antibiotic, nothing but sulfa powder, tourniquets, and the grim mathematics of triage. But they know about penicillin. In 1938, a pathologist named Howard Florey and a biochemist named Ernst Chain, both working at Oxford University, begin reinvestigating antibacterial substances. They are methodical, almost obsessive. They comb through decades of research looking for anything that might work, anything that might have been overlooked. They find Fleming's old paper on penicillin. They find the mold, still alive in Fleming's lab. They begin again where Fleming left off. It takes them 2 years. 2 years of growing mold in bedpans and biscuit tins, extracting tiny amounts of brown powder, testing and refining, and failing and trying again. By 1940, they have succeeded where Fleming could not. They have isolated penicillin in a stable, injectable form. Not much of it, a few hundred milligrams, enough to run a test. May 1940, Oxford. A police constable named Albert Alexander scratches his face on a rose thorn while gardening. The scratch becomes infected. The infection spreads. Within days, Alexander is delirious with fever, his face swollen with abscesses, his blood swarming with staphylococcus and streptococcus bacteria. He is dying, and there is nothing conventional medicine can do. Florey and Chain ask permission to try penicillin. The man's family, desperate, agrees. They inject Alexander with penicillin on February 12, 1941. The response is immediate and miraculous. His fever drops. The abscesses begin to drain and heal. Within 24 hours, he is conscious and eating. Within 4 days, he is sitting up, talking, almost recovered. The doctors are jubilant. Penicillin works. It works beyond their wildest hopes. And then, on the 5th day, the penicillin runs out. Florey's lab has no more. They have used every drop they possess. They even filter Alexander's urine to recover traces of unmetabolized penicillin and inject it back into him. But it is not enough. The infection returns. Alexander relapses. By March, he is dead. The trial is a tragedy and a revelation. Penicillin works better than any drug ever tested, but there is not enough of it. Not nearly enough. To treat one patient for 1 week requires the entire output of Florey's laboratory for a month. There is no industrial process, no way to scale up production. Britain, under bombardment and siege, cannot spare the resources. Its factories are building Spitfires and tanks, not culturing mold. Florey understands that if penicillin is to save lives, thousands, perhaps millions of lives, someone else will have to produce it. Someone with the industrial capacity, the scientific infrastructure, the raw materials and political will to transform a laboratory curiosity into a weapon of medicine. In June 1941, Florey and his assistant, Norman Heatley, board a transatlantic flight to the United States. They carry with them a briefcase and a package of scientific papers. Hidden in the lining of Florey's jacket, smeared into the fabric, are spores of Penicillium notatum. If the plane is shot down, if the luggage is lost, the mold will survive. They are smuggling the future into America. The arrival of Florey and Heatley does not make the front page of any newspaper, but in the offices of the U.S. Department of Agriculture, the National Research Council, and the War Department, it triggers a cascade of decisions that will alter the trajectory of the war. American officials grasp the implications immediately. A drug that can stop infection in its tracks, that can save soldiers who would otherwise die from wounds. Such a drug is not merely a medical breakthrough. It is a strategic asset. Whoever controls penicillin controls the survival rate of their armies. But the United States in the summer of 1941 has no penicillin, not a single vial, no industrial process for making it, no experience with large-scale fermentation of fungal cultures. The pharmaceutical industry has never attempted anything like this. What America does have, what it has in abundance, is a peculiar combination of industrial arrogance and scientific optimism. The belief that if something is possible in a laboratory, it can be made possible in a factory. That mass production is not a question of whether, but of how. In October 1941, officials from the War Production Board convene a meeting with representatives from the largest pharmaceutical companies in America: Merck, Squibb, Pfizer, Lederl, Abbott. The message is blunt. We need penicillin, industrial quantities. We do not care how you make it. We do not care what it costs. Figure it out. Do it fast. The pharmaceutical executives exchange glances. What is being asked of them is not incremental innovation. It is a moonshot. Penicillin in 1941 is produced in quantities measured in milligrams. The military wants tons, but they agree. They have no choice. America is about to enter the war, and soldiers are going to die, and someone has to try. The first problem is the mold itself. Fleming's original strain, Penicillium notatum, produces penicillin in frustratingly small amounts. Florey's Oxford lab achieved yields of about 2 units of penicillin per milliliter of culture broth, enough for research, hopelessly inadequate for mass production. The pharmaceutical companies begin a desperate hunt for better strains. Researchers fan out across the country, collecting mold samples from soil, rotting fruit, old cheese, anything that might harbor a more productive Penicillium variant. The breakthrough comes not from exotic jungle expeditions or cutting-edge laboratories, but from a produce market in Peoria, Illinois. A research assistant named Mary Hunt, tasked with collecting mold samples, visits the local market every week. She inspects tomatoes, bread, overripe vegetables. In the summer of 1943, she brings back a cantaloupe so moldy it is practically collapsing, furred with blue-green growth. The mold is Penicillium chrysogenum, and when cultured and tested, it produces over 200 units of penicillin per milliliter, 100 times more than Fleming's original strain. A moldy cantaloupe from a Midwestern fruit stand becomes the genetic ancestor of virtually all penicillin produced for the remainder of the war. Mary Hunt will come to be known, half-jokingly, as Moldy Mary. The cantaloupe is never preserved. No one remembers which market it came from, but its descendants are kept alive in laboratories to this day. But even the best mold strain is useless without a way to grow it in massive quantities. The Oxford method, surface fermentation in shallow trays, is excruciatingly slow. The mold grows on the surface of a nutrient broth in flat pans, stacked in temperature-controlled rooms. Each tray produces a tiny amount of penicillin. To produce enough for a single patient requires hundreds of trays, weeks of incubation, and constant monitoring to prevent contamination. The U.S. pharmaceutical industry looks at this system and understands that it will never work on an industrial scale. There's not enough space, not enough time, not enough manpower. A different approach is needed, something bold, something unproven, something that might fail catastrophically. Pfizer, a company that made most of its money producing citric acid for Coca-Cola, proposes deep tank fermentation. Instead of growing mold on the surface of shallow trays, grow it submerged in enormous steel vats, tanks holding thousands of gallons of nutrient broth, with sterile air pumped through to keep the culture oxygenated. It is a technique used in the brewing and chemical industries, but never for a biological pharmaceutical. Most microbiologists believe it will not work. The mold, they argue, needs surface exposure to air. Submerged cultures will die or produce nothing. Pfizer's engineers are less certain of failure. In late 1942, they begin construction of the first deep tank fermentation plant in Brooklyn, New York. The tanks are 7,000 gallons each, made of glass-lined steel to prevent contamination. Each tank is fitted with sensors, agitators, and aeration systems. The entire operation must remain sterile. Any bacterial contamination will ruin the batch. The risk is enormous. If deep tank fermentation fails, Pfizer will have spent a fortune on useless equipment. In March 1943, the first tank is inoculated with Penicillium chrysogenum. The engineers and scientists wait. Days pass. The culture grows. Samples are drawn and tested. The mold is producing penicillin, producing it in quantities far beyond anything the surface method could achieve. The deep tank process works. By the end of 1943, Pfizer's Brooklyn plant is producing penicillin in batches of hundreds of billions of units per month. Other companies follow. Merck builds a plant in New Jersey. Squibb expands its facility in New Brunswick. Abbott, Commercial Solvents, and Winthrop Chemical join the effort. The U.S. government pours funding into the program, over $350 million in 1940s dollars, equivalent to several billion today. Factories are built, laboratories expanded, supply chains organized. A network of deep tank fermentation plants spreads across the industrial Northeast, each one producing more penicillin in a week than the entire world produced in 1942. The transformation is staggering. In January 1942, total American penicillin production is measured in millions of units. By December 1942, it is measured in billions. By June 1944, the United States is producing 2 trillion units per month, enough to treat hundreds of thousands of patients simultaneously. The mold that no one wanted in 1928 is now being grown in factories that operate around the clock, tended by workers who do not entirely understand what they are making, only that it is vital that soldiers are dying without it and that every batch must be perfect. The first American soldiers to receive penicillin do not know they are part of an experiment on an unprecedented scale. They know only that they are wounded, feverish, and afraid. North Africa, November 1942. An Army private from Kansas, 19 years old, takes shrapnel to the thigh during an assault on a German fortified position outside Casablanca. The wound is ragged, deep, contaminated with dirt, and cloth fragments driven into the muscle by the force of the blast. In World War I, he would have been evacuated to a field hospital, dosed with morphine and sulfa powder, and left to see whether his immune system could fight off the infection. Odds are, it could not. Within days, the wound would begin to fester. Fever would set in. The leg would swell, turn red, then purple-black, gas gangrene most likely. Amputation at the hip if he was lucky, death if he was not. But this is 1943, and the medical officer attending to him opens a small cardboard box and removes a glass vial of yellowish powder. Penicillin, flown in from a factory in New Jersey 2 weeks earlier. The officer dissolves the powder in sterile saline and injects it into the soldier's buttock. Every 3 hours, another injection. The standard military protocol, developed over months of trial and refinement, calls for a total of 100,000 units per day for 5 days. The soldier's fever breaks on the second day. The wound, cleaned and sutured, shows no sign of infection. By the end of the week, he is walking with assistance. Within 3 weeks, he is back with his unit, limping but functional. He does not think of it as a miracle. Soldiers rarely do. He thinks only that he was lucky, that the shrapnel missed the bone, that the doctors did their job. But the medical officer writes a report. Wounded soldier, compound fracture, contaminated wound, treated with penicillin, full recovery, no complications. The report is filed with hundreds of others, each one a data point, in a vast and rapidly expanding body of evidence. Penicillin works. The evidence accumulates with startling speed. By mid-1943, military hospitals in North Africa, Italy, and the Pacific are routinely using penicillin for combat casualties. The results are revolutionary. Gas gangrene, the infection that caused more amputations and deaths than any other in World War I, is now survivable. Mortality rates for gas gangrene treated with penicillin dropped from 50% to less than 10%, and most of those deaths occur only when treatment is delayed beyond the first 24 hours. Streptococcal infections, wound, sepsis, pneumonia, meningitis all respond to penicillin in ways that sulfa drugs never could. The U.S. Army Surgeon General's office begins compiling statistics. By the end of 1944, they estimate that penicillin has reduced the overall mortality rate from infected wounds by 15% compared to World War I. 15% does not sound like much, but in a war where millions of men are wounded, it translates to tens of thousands of lives saved. But there is still not enough. In 1943, penicillin is so scarce that it is reserved almost exclusively for military use. Civilian doctors watching children die of bacterial meningitis and scarlet fever beg the War Production Board for access. They are refused. Every vial, every dose, every unit of penicillin is allocated to the military. The official policy is brutal in its clarity. Soldiers first. Everyone else must wait. The rationing extends even within military hospitals. Penicillin is not given to every wounded soldier, only to those with serious infections, those for whom sulfa drugs have failed, those whose lives depend on it. Medical officers must justify every dose in writing. Vials are locked in safes. Nurses are instructed to collect the urine of every patient treated with penicillin because up to 80% of the drug is excreted unchanged. The urine is sent to field laboratories where the penicillin is extracted, purified, and reused. The same molecules of penicillin, filtered from the urine of one soldier, are injected into another, and then another, and sometimes a fourth. Nothing is wasted. Nothing can be. There are stories, perhaps apocryphal, but repeated often enough to carry the weight of truth, of medics standing over dying soldiers and making impossible decisions. Two men, both gut shot, both infected. Only one vial of penicillin left. Who gets it? The one with the better chance of survival? The one who is younger? The one whose infection is less advanced? There is no protocol for this. Medics make the choice and live with it. By the spring of 1944, the industrial production of penicillin has reached a scale that seems almost incomprehensible. The United States is now producing enough penicillin to supply not only its own military, but also the British, and to a lesser extent, the Soviet armed forces. Factories in Brooklyn, Terre Haute, and New Brunswick operate 24 hours a day. Workers, many of them women, many of them untrained in anything resembling microbiology, monitor fermentation tanks, harvest penicillin crystals, package vials for shipment overseas. They do not see the soldiers. They see only production quotas, batch numbers, quality control reports. But they understand in an abstract way that what they are making saves lives. The logistics are staggering. Penicillin must be kept cool and dry or it degrades. It must be transported from American factories to ports, loaded onto ships, convoyed across the Atlantic, unloaded in Britain or North Africa, and distributed to field hospitals and aid stations. Every step risks contamination, spoilage, or loss. The military develops specialized packaging, vials cushioned in sawdust, packed in insulated crates, sealed with wax. Penicillin shipments receive the same logistical priority as ammunition and fuel. Entire cargo planes are dedicated to flying penicillin from England to forward hospitals in France after D-Day, June 6, 1944. Normandy, the largest amphibious invasion in history. Thousands of American soldiers storm the beaches under withering machine gun and artillery fire. Men are shot, blown apart by mines, shredded by shrapnel. Medics scramble through the surf and smoke, dragging wounded men to cover. For the first time in the history of warfare, every medic carries vials of penicillin in his aid bag. A rifleman from Ohio takes a bullet through the shoulder. The round exits cleanly, but the wound channel is contaminated with sand and seawater, a recipe for infection. A medic injects him with penicillin before he is even evacuated from the beach. By the time he reaches a field hospital 2 miles inland, he has received a second dose. The surgeons clean the wound, remove bone fragments, stitch the muscle. They administer a third dose of penicillin and send him to a recovery ward. He develops no fever, no infection. Within 2 weeks, he is evacuated to England for rehabilitation. Within 2 months, he is back in the field. In the 6 weeks following D-Day, over 40,000 American soldiers are wounded, seriously enough to require hospitalization. 15% of them, roughly 6,000 men, would have died from infected wounds in World War I. With penicillin, fewer than 500 die from infection. The arithmetic is simple and irrefutable. Penicillin is saving lives at a rate faster than battles can destroy them. German intelligence learns about penicillin sometime in late 1943. Captured Allied soldiers mention it. Medical supplies are recovered from battlefield aid stations. German chemists analyze the samples, identify the compound, and attempt to replicate it. But Germany, by 1943, is a nation under siege. Its cities are being bombed, its factories repurposed for tank production and munitions, its supply lines stretched across occupied Europe and collapsing in the east. There are no resources to build fermentation plants, no industrial capacity to spare for pharmaceutical research. A handful of German scientists working in makeshift laboratories managed to produce small amounts of penicillin, enough to treat a few dozen patients. But there is no industrial production, no distribution system, no supply chain. German soldiers continue to die from infected wounds at rates comparable to World War I. In field hospitals on the Eastern Front, where conditions are nightmarish and antibiotics are almost non-existent, infection kills more German soldiers than Soviet bullets. Some German prisoners of war captured by American forces in 1944 and 1945 are treated with penicillin in Allied hospitals. A Wehrmacht officer, captured during the Battle of the Bulge with a shattered leg and spreading septicemia, is injected with penicillin by an American medic. He expects nothing. He has been told that prisoners receive minimal treatment, that the Allies are as brutal as German propaganda claims. Instead, his infection clears. His leg is saved. He is transferred to a POW hospital in England where he is fed regularly, treated with the same medicine given to Allied soldiers, and allowed to recover in warmth and relative comfort. He does not speak much about it after the war, but in letters written decades later, he describes the penicillin as the moment when he understood that Germany had lost, not because of tanks or airplanes or superior tactics, because the Americans could afford to heal their enemies. because they had so much medicine, so much abundance, that they could spare it even for men who had been trying to kill them. By the end of 1945, the United States has produced over 650 billion units of penicillin. The number is almost meaningless in its enormity. 650 billion units is enough to treat millions of patients, enough to supply every military hospital on every front, enough to stockpile for the occupation of Germany and Japan, and it is enough, by the war's end, to begin releasing supplies for civilian use. In 1945, penicillin becomes available to American civilians for the first time. A mother in Des Moines whose child has bacterial meningitis, a death sentence in 1940, can now walk into a hospital and receive penicillin. The child will survive. A factory worker in Pittsburgh who cuts his hand on a lathe and develops blood poisoning can be treated and cured. Syphilis, a disease that once ravaged slowly over years, can be cured with a single course of injections. The impact on public health is immediate and profound. Mortality from bacterial infections, which had declined slowly over the previous decades due to improved sanitation and sulfa drugs, plummets. Pneumonia deaths drop by over 60% within 5 years. Maternal mortality from puerperal fever caused by streptococcal infection after childbirth nearly disappears. Scarlet fever, diphtheria, bacterial meningitis all become treatable, survivable, routine. Children who would have died live. Mothers who would have been widowed are not. A generation grows up in a world where infection is no longer a death sentence, where a cut or a fever is an inconvenience rather than a catastrophe. They do not remember what came before, but their parents do. Their grandparents do. The scientists who discovered and developed penicillin are celebrated. Alexander Fleming, Howard Florey, and Ernst Chain are awarded the Nobel Prize in Physiology or Medicine in 1945. Fleming becomes a celebrity, his face on magazine covers, his name a household word. He gives speeches, receives honors, is knighted by the British Crown. In interviews, he is modest, self-deprecating, quick to credit luck and accident for his discovery. Florey and Chain, who did the harder work of isolating and testing penicillin, receive less public attention but equal recognition from the scientific community. Florey, in particular, is credited with the vision to bring penicillin to America, to transform it from a laboratory compound into an industrial drug. But the engineers who built the fermentation tanks, the workers who tended the mold cultures, the chemists who refined the extraction process, the truck drivers who transported the vials, the military logistics officers who organized the distribution. These people are not remembered. Their names do not appear in textbooks. There are no Nobel Prizes for factory workers, yet it is their labor, as much as Fleming's accidental discovery, that saved 100,000 lives. Penicillin was not invented by a single genius in a moment of inspiration. It was built slowly, methodically, by thousands of people working in parallel, each contributing a small piece to a vast and intricate system. The mold that Mary Hunt found on a cantaloupe, the deep tank fermentation method pioneered by Pfizer's engineers, the quality control protocols developed by military chemists, the medics who injected soldiers on beaches and in jungles, who collected urine and recycled the drug, who made impossible decisions and lived with them. Penicillin is not a miracle. It is the result of a civilization, a specific civilization, at a specific moment, deciding that no effort was too great, no expense too high, to save the lives of its soldiers. There is a photograph taken in 1944 of a penicillin production facility in Brooklyn. It shows rows of fermentation tanks, each one 10 feet tall, stretching back into shadow. Workers in white coats and cloth caps stand between the tanks, adjusting valves, checking gauges. The air is hazy with steam. The room is lit by industrial lights hanging from the ceiling, casting harsh shadows. It does not look like a place where miracles are made. It looks like a factory, and that is exactly what it is. The symbolism of penicillin, if one can speak of such things in terms of symbol, is the vial itself, small, glass, filled with a yellowish powder that weighs almost nothing. A medic can carry a dozen vials in his jacket pocket. Each one represents months of labor, thousands of gallons of culture broth, the coordinated effort of scientists, engineers, factory workers, and logistics officers. But to the soldier, it is simply medicine. He does not see the factory, the fermentation tanks, the chemists in their laboratories. He sees only the needle, the injection, and then if he's lucky, the slow return of strength and clarity. The vial is a compression of American industrial might into a form so small and mundane that it is easy to overlook, but it contains within it the capacity to reverse death. To take a man who is dying from infection, a man whose blood is poisoned, whose organs are failing, whose hours are numbered, and return him to life. This is not metaphor. This is documented medical fact, repeated tens of thousands of times across battlefields and hospitals on 3 continents. By 1950, penicillin is so common that it is prescribed for minor infections, ear infections, sore throats, infected cuts. The drug that was once worth its weight in gold is now mass-produced and inexpensive. A course of treatment costs a few dollars. Pharmacies stock it as routinely as aspirin. The generation that fought the war remembers when it was different. They remember when infection meant death, when a wounded soldier's greatest fear was not the wound itself, but what came after. They remember when penicillin was rationed, hoarded, recycled from urine, because every unit was precious. And some of them, those who were wounded, who were treated, who survived when they should not have, carry with them a memory more visceral than statistics or history books can convey. The memory of fever breaking, of pain receding, of waking in a hospital tent, weak and disoriented but alive, and knowing that something impossible had happened. A sergeant from Tennessee, wounded during the Battle of the Bulge, writes in a letter home, "I do not know what they gave me, but I was dying, and then I was not. The docs said it was a new medicine, something called penicillin. I do not understand it. I only know that I am alive, and I should not be." He is not a poet. He is a farm boy who enlisted in 1942 and spent 3 years in Europe. But his words capture something essential, the incomprehensibility of survival. When death seems certain, sir. The strange dislocating experience of being saved by something you cannot see, cannot understand, but which works nonetheless. In the end, the story of penicillin is a story about time and scale. Fleming discovered the moldy things, moltindain, 1928, but the world was not ready. Florey and Chain revived it in 1939, but Britain could not produce it. It took the United States, America in 1941, facing global war and driven by necessity to transform a fragile laboratory curiosity into an industrial weapon. And it is a story about what a society chooses to value. The decision to pour hundreds of millions of dollars into penicillin production was not inevitable. Resources could have been allocated elsewhere. More tanks, more planes, more bombs. But American military planners and political leaders made a choice that saving soldiers' lives was worth the investment, that medicine was as important as munitions, that a wounded man was not expendable. This choice was not purely humanitarian. It was strategic. Soldiers who survive their wounds can return to combat. An army that can treat infections effectively can sustain longer campaigns with lower casualty rates. Penicillin gave the Allies a tangible, measurable advantage, not in firepower or mobility, but in survivability. But strategy alone does not explain the scale of the effort. Something else is at work. A belief, perhaps, that American power is measured not only by its capacity to destroy, but by its capacity to heal. That abundance is not just material wealth, but the ability to save lives on an industrial scale. The German prisoners of war treated with penicillin understood this in ways that are difficult to articulate. They had been told that the Allies were weak, decadent, incapable of sustaining a long war. They had believed that German discipline, German engineering, German willingness to sacrifice would prevail. And then they were captured, wounded, dying of infections. And they were given medicine that their own army could not provide. Some interpreted it as mercy, others as propaganda, a calculated gesture to win hearts and minds. But a few, the more perceptive ones, understood it as something else, a demonstration of industrial and scientific supremacy, so total that the Americans could afford to heal even their enemies. One German officer captured in 1945 and treated for pneumonia at a POW camp in Texas later wrote, "I realized then that we had lost not because we were weaker in spirit, but because they were richer in everything. Richer in food, in machines, in medicine. They did not need to let us die. They had so much that they could afford to let us live. It is a cold calculation, stripped of sentiment, but it is not wrong. There is a cemetery in Normandy where American soldiers are buried. Row after row of white crosses stretching across green hills overlooking the sea. 9,000 graves. Most of the men buried there died in combat, shot, shelled, blown apart in the chaos of the invasion and the months of fighting that followed. But there are graves that are not there. Thousands of them. Men who would have been buried in that cemetery if they had fought in World War I, when infected wounds killed as reliably as bullets. Men who were wounded at Omaha Beach, or in the hedgerows of Normandy, or in the Hürtgen forest, and who received penicillin in time, and who lived. Those men went home. They married, had children, built lives. Their children do not think of them as survivors of penicillin. They think of them as fathers, grandfathers, men who came home from the war and did not talk much about what they had seen, But those men know. In quiet moments, in the privacy of their own thoughts, they know that they were dying and something saved them. A vial of yellowish powder, dissolved in saline, injected by a medic whose name they never learned. Penicillin, in the end, is not a symbol of American democracy or freedom. It is not a metaphor. It is a physical substance, a collection of molecules with a specific chemical structure produced by a fungus and refined by human ingenuity. It kills bacteria. That is all it does. But what it represents, what it has come to represent, is the capacity of a society to mobilize its resources, its science, its industry toward the preservation of life, to take a problem that seems insurmountable, millions of soldiers, tens of thousands of infections, inevitable death, and solve it through sheer force of will and organization. The Germans had discipline. The Japanese had courage. The Soviets had endurance. But the Allies, and America in particular, had something that could not be matched: the ability to turn the impossible into the routine, to industrialize miracles, to produce in such overwhelming quantities that even their enemies could be saved. 100,000 soldiers. That is the estimate. 100,000 men who would have died from infected wounds who instead lived. It is a number too large to comprehend as individuals, but small enough to matter. It is a generation of fathers, a city of sons, decades of life stretched forward into peace. And it began with a moldy petri dish, an open window, and the stubborn refusal to accept that anything, even death itself, was beyond the power of human effort to overcome.